Hello and welcome to our lesson on solving exponential and log equations. So we've looked at one section of solving exponential equations, but the exponential equations that we looked at were equations where we could get a common base on both sides. So for instance, if we're looking at problem number 1 here, if I had, 3 to the x power equal to 9, this isn't a big deal because these share a common base. 3 and 9 are both powers of 3. So if I left this side as 3 to the x and rewrote 9 as a power of 3 as well, so 3 squared, then once those bases are the same, they no longer affect the problem. Those exponents would have to be equal, and so we'd have our solution of 2. Not that that process is required for something that simple, but we can't use that same process here because 3 and 10 don't have a common base. So if there isn't a base in common, what do we do? Is what we're going to look at today. Now, the process I'm going to show you today isn't always going to work. There are other types of log equations exponential equations where we can't get a common base, and we can use logarithms to solve, but that's something we're going to work toward. Today, what we're going to do is use a property of logarithms that we talked about in the previous topic. So remember, we said if we had something like, let's say, a to the b power equals x, that we could rewrite that. We could say the log, I don't want to use these letters this way. Sorry. Let me try this again. If I had, let's say, b to the x power equal to y, I could say the log base b of y is equal to x. Although, I don't know why I switched those letters. I don't know, didn't like the way it looked. It doesn't matter what letters you use. You can go from exponential to log form or vice versa in keeping the base of the exponential as the base of the log. And then remember, the exponent here is the answer to the log here. And then the argument of the log is the answer here. Okay? So we got to be able to go back and forth from log form to exponential form. That's the key in the process we're going to be looking at today. And if we want to evaluate a logarithm, some of them I'm hoping we can do by hand, or just by looking at it and understanding some of our exponents, but Desmos can evaluate any log for us as well. So you can use Desmos to find the value of any logarithm. Okay, so what we're going to do is use that rewriting process to solve. Okay, we're going to use the rewriting process to solve. So think about this number 1 again. I can't rewrite both sides with a common base, but what I'm looking for here is a power, and that's exactly what a logarithm is. If I rewrote this in log form, it would be the log base 3 of 10 equals x, where the x that I'm trying to solve for is the answer to my logarithm. So all I have to do is evaluate what I have here. Oops, I'm going to get this. All I have to do is evaluate what I have here to solve, right? X is already solved for once it's rewritten. So it's a matter of going to the calculator from there. So we want to try to rewrite these exponential equations in log form, but it might be necessary to get the exponential piece by itself first. So for example, in number 2, you see how there's 2 times the exponential piece? If I rewrite this in log form, there's no spot for that extra coefficient. So if we have anything extra in our equation, like a times 2 or something plus 1, we want to get rid of that first so that I have a base, I have an exponent, and I have something after the equal sign. 3 things are what we need to rewrite, 3 pieces. If we have anything extra, there's no spot for it in the rewriting. We've got to get rid of that first. So if necessary, we're going to isolate the exponential piece of the equation. That means let's get it by itself. Okay, and then again, rewrite the equation in log form. And we can use Desmos to evaluate. And the nice thing is, we can check our work too at the end of solving. Sometimes after the evaluating piece, we're going to be finished. We might have to continue to solve for x in a couple of these, but I'll show you. Okay, but the nice thing is we can always use Desmos, plug things back in, and check to verify that we're doing these things properly. Okay, so let me go back to this one. Again, I can't just rewrite these with the same base, but I can like 3 to the x equals 9. I can't get common bases there, but I can rewrite this in log form. A log is a power, and I'm looking for some power of 3 to get me 10. Now, I can approximate this. Because I know 3 squared is 9, I know the power I'm looking for is going to be a little bit more than 2 because I'm trying to get to 10 instead of 9. So I know the decimal approximation is going to be a little over 2, but I find that using a log. So rewriting this again is going to be the log base 3 of 10 equals x. And now it's just, oops, go to the calculator from there. So my calculator, remember, we go into functions, and in miscellaneous, you're going to find the log, and we want to choose the one that allows us to change the base. So log base 3 of 10 is about 2.095, so let's just say about 2.1. So x is approximately 2.1, which is what I anticipated in the beginning. Okay, now looking at number 2, again, the exponential piece, this 5 to the x, is not alone. It's being multiplied by 2. So I'm going to start this one by getting rid of that 2. I'm going to divide both sides by 2. So that's going to cancel that there. And now I have 5 to some power equal to 64. Now there is no common base for 5 and 64, so I can't use that process we talked about in our first topic. And let's see, if I was trying to estimate here, I know 5 squared is 25. I know 5 cubed is 125. I'm looking for 5 to some power to get me 64, which is right in between those two. So I know I'm looking for a decimal that's going to be between 2 and 3. But the only way to figure out exactly what that power is to use a log. So if I rewrite this, this would be the log base 5 of 64 equals x. That is, what power of 5 makes 64? Well, we can approximate that. So we go to Desmos and we say, what is the log base 5 of 64? And it tells us it's about 2.6, which is what I anticipated again in the beginning. Okay, and if you want to keep more of the decimal, it'd probably be a little more accurate, but since it doesn't really specify where around here, then it's like, who cares, right? No. We can be a little more accurate with more of the decimal, but I just want you to get the process here, okay? Now looking at number 3, our base is different. Now it's different in all these, right? Base of 2, base of 5, but when we have a common number, we're going to use the common logarithm. When our base is e, we want to use the natural logarithm because natural logarithm is already base e. So I'm looking for e to some power to be 42. If I use the natural log, rewrite this with a natural log base e of 42 equal to x, then it's a little less to put into the calculator. Now I rewrote it, writing the base of e there just so you know that base is still that base, but natural log is already base e, so I don't have to write that. So that is really just the same thing as the natural log of 42 equal to x. So we're going to approximate this using our natural log. So what is the natural log of 42? It's about 3.7. So it's about 3.7. Okay, so anytime you have a base of e, use the natural log. Use natural log for base e. Okay? All right, let's try another one. If you notice in this one, we have an extra bit in our exponent. This is where we're going to have to continue to solve for x after we rewrite. But we've got 3 spots, right? 3 pieces here. So we're good to rewrite this. This is going to become the log base 2 of 30 equal to 2x. So if I want to solve for x here, x is being multiplied by 2. That times 2 just makes one extra step. So what I would do next is go ahead and divide that 2 over to get rid of it. So x is going to be exactly the log base 2 of 30 divided by 2, which we can approximate now using Desmos. So let's put in, again, log base 2 of 30, and then I want that to be divided by 2. So we're at approximately 2.45. I'm just going to say 2.5. And if I wanted to just be sure and check this, let's see, 2 raised to the 2 times, now I'm rounding this, so let's just say 2.45 here. I get 29.8. It's not exactly 30, but that's because my answer is rounded, but I can still verify that I'm getting close with that approximation. Okay? And here, again, we want our exponential piece to be by itself before we do anything. And so The first step here is to get rid of this plus 7 by subtracting it over, because there's no spot to put that when I go to rewrite. So that's going to leave me with 3 to the 4x power equals 18. Now again, no exact power of 3 is going to get me 18, so I'm going to rewrite this. I'm going to make this the log base 3 of 18 equal to 4x. And so if I want to solve for x, I'm going to have to divide both sides by 4. So x is going to be exactly the log base 3 of 18 divided by 4, which we're going to approximate using Desmos. So log base 3 of 18 is going to be divided by 4, and this is about 0.657, let's just say about 0.66. Okay, now when you're working in your assignments in Canvas, I'm going to have to probably have you approximate, so you're going to need to get the decimal. Although, if I ask you to input an exact answer, you should be able to do that too. So just so we can distinguish, and I haven't done this yet, this would be the exact answer. If you're asked to put in an exact answer, that means I want to see it with logarithms in it. If I ask you to approximate the answer, then you're going to go ahead and give me the decimal form. So either one of those could be asked. Be prepared to give either one. And here's one for you to try. Okay, so if you're feeling confident with this so far and you want to give the next one a shot, pause the video and try it out. So there's a plus 1, but I can't get rid of that plus 1 first because it's with the exponent. So I'm going to go ahead and rewrite this. This is going to be the log base 7 of 50 equal to x plus 1. So if I want to solve for x, I can get rid of the plus 1 now by subtracting it over. So my exact answer would be a log base 7 of 50, which I want to make sure all stays together, minus 1 equals x. And again, that's something that we can approximate using Desmos. So we have log base 7 of 50, and then after that I want to subtract 1, and so I have about 1.01 for my approximation. And there it is, not so bad. Okay? So we're here, we have an application problem, and we're going to do some more applications toward the end of the unit here, but just so you can see one spot where something like this could be applied. It says the population of a city is growing exponentially, and the number of people y in the city can be calculated with this growth model, y equals 3,000 times 1.12 to the x power, where x is the number of years. It says about how long is it going to take for this population to double? So it says here that y is the number of people, the number of people is y, and that x is the number of years. So it's asking you how long, that means we want to figure out an x value, is going to take for the population to double. So if the population doubles, then what is it going to be? Oh, this is, guys. Okay, so there's something that, there's a little underlying knowledge you have to have here in order to do this, and it relates to exponential functions, which I just had a brain fart here. We haven't done exponential functions yet. Okay, so the starting population happens to be 3,000. That's something that we're going to learn about reading an exponential function, understanding where it starts. So initial population is 3,000. You're just going to have to go with me on this for now. So your population doubling means that we're trying to figure out when it's going to get to 6,000. So y equals 6,000. And I'm sorry. My apologies for putting this in here. I changed the order in which I normally teach these things, so I should have taken this question off, but it's okay. Let's go with it for now. We want to find an x value when a y value is 6,000. So how do I find one of the values when I know the other? Well, we're going to plug in. So we're going to put the 6,000 in for y, and we have 3,000 times 1.12 raised to some power. So we're trying to solve for x when we know y is 6,000. We plug in the variable we know and solve for the one that's left. This is what we were just doing. If we divide both sides by 3,000, then we can get the exponential piece by itself, and 6,000 divided by 3,000 is going to be 2. So 2 equals 1.12 to the x power. And now I can rewrite this. This will be the log base 1.12 of 2 equal to x, which we can now approximate using our calculator. So log base 1.12 of 2 is going to be about 6.116, so this is about 6.11. So this is going to be a little over 6 years for the population to double. Okay, now once we get to the end of the unit, again, we'll talk more about those functions and you'll understand why the initial was 6,000 or 3,000. My apologies again for putting that in there. If I just asked the question a little differently, then we would have been all right. But we're going to see more applications toward the end of this, so don't freak out if that one was a little bit tricky. I'll be a little more clear if I put something like that in your practice, okay? So those were exponential equations. What we're going to look at next are log equations. So where your equation starts with a logarithm, and sometimes solving a log equation doesn't actually require any solving. So for example, in number 1, it's technically a log equation, but there's nothing to solve for because x is already by itself. So just evaluate if x is already alone. If it isn't, then if x is not alone, then we're going to do the reverse of what we were just doing. We're going to go ahead and write this in exponential form to solve. So if it's a log, or if it's exponential, we can rewrite it with the log. If it's log, then we can rewrite it with an exponential and try to go from there. So this is something that we can evaluate. X is already by itself on number 1. So what is the log base 4 of 50? It's approximately 2.8. So we're going to say x is approximately 2.8. Nothing to solve for there. X is already by itself. But if we look at this next one, oh, we can do this one too. Just evaluating here. Now, I would argue, yeah, well, let's put it in the calculator. I'm going to argue something with myself here. If we put this in the calculator, log base 4 of 0, it says that it's undefined. So think about what this is saying. When you're reading this log base 4 of 0, remember you're looking for 4 to what power gets you 0. Well, it isn't possible to raise a number to a power and get to 0. So if you raise to the 0 power, you get 1. If you raise to a negative power, remember it just moves it to the opposite side of the fraction. So what's going to happen is it's not going to be possible to raise something to a power and get it to be 0. You can make fractions that are infinitely small, but you can't get it to be 0. So this is undefined. This expression is undefined. So that means there is no solution to this equation. And we're going to, again, this will make a little more sense when we talk about the functions. I guess I should have put that lesson first, but it is what it is now. The argument of a log can't be 0. You cannot raise a base to a power and get it to be 0. So the argument of a log cannot be 0. Because you can't raise something to a power and get it to be 0, so this will never be defined. Can't be 0. Okay. Now let's look at another one. This is one where we actually would have to do some solving here. Simple solving, but solving because x is not by itself. So the log base 5 of x equals 3. If I rewrite this one in exponential form, this would be the base of 5 raised to the power of 3 equals the argument of x. Once I've rewritten it, it's solved. X is all by itself, so it's a matter of going to the calculator if you need it, but hopefully you know that 5 cubed is 125, so 125 is our solution. Okay, or here, this does require you knowing that the natural log is base e. So if we have natural log, I'm like so zoomed here. If we have the natural log, goodness, just so you can see it, this is the same thing as the natural log base e of x equal to, when you go to rewrite this, this is e squared equal to x. Once it's rewritten, again, x is solved for. So we just need to figure out the value of e squared. So we're going to put in to Desmos e squared, and it's going to tell us that that's about 7.4. Oh my goodness. 7.4. I'm all over the place here. Okay, next, one for you to try if, again, you're feeling pretty confident with this. We're just trying to rewrite it. This becomes 8 to the 2/3 power equal to x. Now that it's rewritten, x is solved for. Now, again, I would hope that this is something you could evaluate without a calculator. Let's go ahead and go to it, though. If we put in x 8 to the, sorry, I don't know why I said x, 8 to the 2/3 power, 2/3 is your exponent, you get 4. Now, why does this end up being exactly 4? Remember, 8 to the 2/3 power is equal to the cube root of 8 squared, and the cube root of 8 is 2, and 2 squared makes 4. Okay, so some old stuff coming back here, but you do have a calculator that will evaluate for you, so not to worry. All right, now number 5 looks a little more challenging because I put a little more in there, but same process. If I rewrite this, this becomes 3, the base of 3 to the power of 3 equals the argument, which is, in this case, x plus 1. So 3 cubed on this side is 27. If I want to solve for x, it's just one extra step. Let me subtract 1 from both sides, which means x has to be equal to 26. No big deal, 26, okay? And here, remember that when you don't see the base on the common log that it's 10, so this is really just saying log base 10 of x squared equals 2. So if I go to rewrite this, it's 10 squared. 10 squared equals x squared. So what number can we square to get 10 squared? Well, actually, there are two results here. 10 squared is 100, right? So what number can we square to get 100? Technically, a positive 10 and a negative 10. So x can be equal to plus or minus 10. Okay, plus or minus 10 squared is equal to 10 squared. All right, and again, one for you to try if you're feeling all right with this so far. So pause the video and give it a shot if you can. If not, when I rewrite this, it's 4 squared. So 4 squared equal to our argument, which is x minus 3 over 2. Now 4 squared is 16, so I'm going to make this side 16. Sorry, space that a little better. 16 equal to x minus 3 over 2. And then to solve from here, I would get rid of the divide 2 by multiplying both sides by 2. So now I'm left with 32 equal to x minus 3 because these cancel, right? And now I can add 3 to both sides, which tells me x has to equal 35. So 35 equals x is my solution here. Okay, not so bad. And again, if you wanted to check any of your work, feel free to do that. So let's say I wanted to check this one, log base 4 of, if I put in 35 minus 3 over, nope, let's make the fraction here. 35 minus 3 over 2. I get the 2 that I have on the other side of the equation. So if at any point you want to check your work, remember you can always plug back in to do so, and you don't even have to do that by hand. Your calculator will do it. All right, how about this guy? This one, if we rewrite, we would have x squared equal to 48. And how do we solve this? We know we take the square root of both sides, and so x is going to equal technically plus or minus the square root of 48. Now the square root of 48 can be simplified. If we break down the 48, it's 2 times 24, and then 2 times 12, and then 2 times 6, which means a 2 will come out, and sorry, 6 breaks down, another 2 will come out. So we're looking at x equal to plus or minus 4 radical 3 for our exact solutions. Okay? And lastly, again, if you feel like this is something you can handle, give it a shot. Rewriting here becomes x squared. X squared equals the argument, which in this case is 2x plus 3. So another quadratic to solve, but I can't use the square root method like I did on the other one because I have got two terms with variables here. So in this case, I'm going to subtract over the 2x and subtract over 3 to make it all equal to 0 and see if I can factor. And in fact, I can. Factors of -3 that make -2 would be -3 and +1. And this thing is then going to factor into 1x minus 3 and 1x plus 1 equal to 0. And that means we get a solution of 3 and we get a solution of -1. So 3 and -1 are both going to be solutions for this equation. Okay, so not so bad, hopefully. Just rewriting. If it's log form, put it in exponential form. If it's exponential form, put it in log form. Now there will be more challenging exponential equations and more challenging log equations where we're going to have to take a different approach. But this is the approach you should be looking for first because it's the simpler approach. And I'll show you at the end how to differentiate between. But for now, I think you have enough to work on to get through this practice assignment. But as always, if you need some extra help, then just reach out. All right, guys, take care.